Forget everything you thought you knew about perpetual motion. Magnetic motors are real, and they could be about to change the way we power our vehicles forever. We're diving into one of the most debated, controversial, and fascinating concepts in the world of energy innovation. Is it science or science fiction? Can a motor truly run forever without any external energy input? The idea is bold, seductive, and for many, absolutely irresistible. A machine that powers itself, generating clean energy without fuel, emissions, or limits. It sounds like something out of a utopian novel, but inventors around the world have been chasing this dream for over a century. From backroom tinkerers to PhD engineers, the idea of a magnetic motor has inspired thousands. But what exactly is a magnetic motor? At its core, it's a device that uses magnets, usually permanent magnets, to generate rotational force. This rotation is then theoretically used to create electricity or perform work, all without needing an external fuel source. The principle appears simple. Magnets repel or attract, and that force can be manipulated. If you arrange the magnets in the right way, can you create continuous motion? That's the million-dollar question. To many, the concept represents the holy grail of free energy, an answer to global energy concerns, a path to ending fossil fuel dependency and environmental degradation. But to others, it's pure pseudoscience, an impossible fantasy that violates everything we know about physics. So where does the truth lie? To understand this, we need to travel back in time. The fascination with perpetual motion didn't start with electric vehicles. It dates back to ancient civilizations. Early inventors like Bhaskara in the 12th century conceptualized wheel-based devices that would rotate forever. In the 17th century, overbalanced wheels and magnetic spinners became popular among European inventors. The Industrial Revolution further fueled this curiosity. As machines became more widespread, so did attempts to make them run endlessly. By the 19th century, magnetic motors were part of the conversation. Inventors started incorporating permanent magnets in their prototypes. The allure was always the same: unlimited motion, unlimited energy. Yet each attempt hit the same wall: friction, resistance, losses. No matter how perfectly designed, every machine lost energy over time. The magnetic motor, despite its elegance, proved no exception. It would slow down. It would stop. Still, the dream didn't die. In fact, it only evolved. As electric vehicles emerged as the next frontier in transportation, magnetic motor theories resurfaced with new urgency. Range anxiety became a dominant concern among consumers. How far can I drive before I run out of charge? Will I find a charging station in time? What if the battery fails? These fears are valid and widespread. While modern EVs offer impressive ranges, they still fall short for many. And so the idea of a self-powering motor became a tantalizing solution. Could a magnetic motor, even if not truly perpetual, extend the range of an EV significantly? Could it reduce reliance on charging infrastructure? Could it make electric cars more appealing to the masses? To answer that, we must revisit the science. The first law of thermodynamics is clear: energy cannot be created or destroyed. This means that for a magnetic motor to run, it must draw energy from somewhere, even if that energy isn't visible, like stored kinetic motion or environmental input. There's no such thing as a truly isolated system in the real world. Frictional losses occur in every rotating object. Air resistance, material friction, electrical resistance, they're all inescapable. Magnets themselves degrade over time. Even permanent magnets can lose their strength. Heat buildup also becomes a major factor in moving systems. So how can a magnetic motor overcome these obstacles? That's the central challenge. The most advanced designs attempt to use clever geometry. Magnets placed at strategic angles repelling in sequence. As one magnet pushes, the next one aligns to keep the motion going. Some systems use additional components like flywheels or stators. Others incorporate regenerative feedback loops. Yet even these sophisticated attempts fall short of perpetual motion. They may run for minutes, even hours, but never forever. And when it comes to powering a vehicle, almost isn't good enough. Still, advocates of magnetic motors point out an important nuance. They argue that we don't need true perpetual motion to make a difference. We just need dramatically increased efficiency. Even if a magnetic motor can only reduce battery usage by 30%, it's a massive gain. That could mean longer trips, fewer charging stops, and more affordable EVs. So, is there room for compromise? Instead of debating whether magnetic motors can defy physics, we should ask how they can enhance real-world systems. This is where the research gets interesting. Universities and private labs are studying magnetic field dynamics with renewed intensity. Superconducting magnets have opened new possibilities. These materials conduct electricity with near-zero resistance at extremely low temperatures. Imagine combining that with a motor design that maximizes magnetic repulsion. The potential torque output could be immense. Efficiency could leap far beyond current electric motors. But again, it wouldn't be free energy. It would be smarter energy use, and that distinction matters. Let's consider the mechanics of an electric vehicle. Most EVs today use induction or permanent magnet synchronous motors. These are incredibly efficient, up to 90% in ideal conditions, but they still rely on battery power. They still generate heat and experience where a magnetic enhancement system could work alongside them. It could serve as a booster during acceleration or uphill climbs. It could reduce load on the battery in stop-and-go traffic. It might even generate power through regenerative braking more effectively. But none of this is new energy. It's simply redirected or reused energy. And that brings us to the harsh reality of physics once more. Every bit of energy must come from somewhere. The magnetic motor, no matter how elegantly designed, must obey this rule. So does this mean we should abandon the idea entirely? Not necessarily. Sometimes failed concepts lead to real breakthroughs. Many early magnetic motor experiments led to advances in magnet materials. Others inspired new motor topologies. Some even contributed to better battery management systems. Innovation doesn't always come from success. It often comes from bold failure. In fact, some of today's most cutting-edge EV motors have roots in these early experiments. The fascination with magnetic motors has pushed engineers to rethink fundamental assumptions. What if the magnetic motor isn't a power source, but an efficiency multiplier? What if it's part of a hybrid system, complementing batteries and solar input? This hybrid model could be far more realistic and impactful. Some experimental EVs are already testing this idea. Their designs include magnetically assisted flywheels that store and release energy. Others integrate linear magnetic actuators that replace traditional mechanical linkages. These innovations reduce friction and increase system life. They don't break physics, they work within it creatively. And perhaps that's the lesson we need. Chasing perpetual motion may be a dead end, but chasing higher efficiency isn't. The public's desire for magnetic motors is rooted in a deeper truth. We want energy independence. We want sustainable transportation. We want freedom from fossil fuels and unreliable grids. A magnetic motor may not be a magic bullet, but it's a symbol of that desire. And symbols can drive real change. It inspires students, engineers, and dreamers to keep exploring. Even if they never find a perpetual motor, they may find better batteries, better converters, better EV architectures. And that's how science moves forward. Not by ignoring the laws of physics, but by pushing up against them. By testing the limits, by asking bold questions, even if they sound foolish at first. The line between genius and delusion is thin, but it's often where breakthroughs are born. So if you're wondering whether magnetic motors are real, yes, they are, but not in the way most people hope. They don't run forever. And they hold potential, not for endless energy, but for more efficient energy use. That's the real takeaway. The goal isn't to cheat physics, it's to innovate within it, to create systems that are smarter, not magical. And in that pursuit, the magnetic motor still has a role to play. A supporting role, not a starring one, but valuable nonetheless. To continue our journey through the world of magnetic motors, we need to shift our focus to the present and future. Right now, engineers and researchers are working on practical applications of magnetic technology in electric vehicles. They understand the constraints of thermodynamics and conservation laws. They also understand the immense potential in refining how energy is managed, transferred, and recovered. This means pushing magnetic motor designs away from the realm of fantasy and closer toward functional innovation. These are not standalone motors that claim to run perpetually. Instead, they are built to optimize the interaction between magnetic fields and rotational dynamics. One example involves using Halbach arrays, a special arrangement of magnets. This configuration focuses magnetic fields on one side while canceling them on the other. It allows for more concentrated and directional magnetic force. In a motor, this means greater torque with less wasted energy. Such motors are already in use in magnetic levitation systems and are being tested in EV prototypes. They can deliver powerful acceleration without needing heavy electrical input. They're not infinite energy machines, but they're more efficient ones. Efficiency is the key word here. The more efficient a motor, the less energy it wastes as heat or vibration. This directly translates into longer battery life and extended vehicle range, and that's the real solution to range anxiety. Not magic, but efficiency. Their flat, disc-like structure allows for shorter magnetic paths and reduced weight. They're lighter, smaller, and can achieve higher power density. When combined with permanent magnet enhancements, axial flux motors become incredibly efficient. Several EV startups are exploring these designs for next-generation vehicles. These motors may not eliminate range anxiety entirely, but they can dramatically reduce it. Less energy wasted equals more miles driven. That's a simple equation everyone can understand. Let's also examine regenerative braking systems. This technology captures kinetic energy during braking and converts it back into electricity. Magnetic fields are crucial to this process. As the wheels slow down, motors function in reverse to generate current. It's a brilliant feedback loop that helps recharge the battery while driving. Some concept vehicles are testing magnetically enhanced systems to improve regeneration rates. More electricity captured per stop means greater range overall. Again, it's not about creating energy from nothing, it's about recovering energy that would otherwise be lost. Another innovation on the horizon is wireless magnetic charging. While unrelated to motion itself, this technology uses magnetic resonance to transmit energy without cables. EVs could charge while parked or even while driving on specially equipped roads. Magnetic fields play a starring role in this concept. If perfected, it could eliminate range anxiety entirely, not by changing motors, but by changing infrastructure. Charging becomes invisible, constant, and automatic. No stops, no cables, no stress, and all of it powered by controlled magnetic interactions. Some highways in Europe and Asia are already testing these systems in pilot programs. Even if the magnetic motor doesn't run forever, the ecosystem around it could. An ecosystem where magnetism enables not just motion, but mobility. But let's return to the core debate for a moment. Many people still believe magnetic motors can be perpetual. There are countless YouTube videos, forum threads, and patent filings that claim breakthroughs. Some show spinning rotors that seem to go on endlessly. Others feature complicated gear systems powered solely by magnets. Are these hoaxes or misunderstood genius? In most cases, they're misinterpretations or outright scams. Hidden batteries, hidden motors, and selective camera angles are common tricks. In other cases, the motion is real but temporary. A well-balanced rotor can spin for a long time, especially with low friction, but eventually it always stops. Yet the persistence of these beliefs reveals something deeper. People want to believe. They want to hope for a miracle solution to the energy crisis. And that hope drives curiosity, which isn't a bad thing. Curiosity fuels experimentation. Experimentation leads to understanding. Understanding leads to real progress. And that's where we must draw the line between hope and hype, between science and speculation, between belief and evidence. The real advances in magnetic motors are happening quietly in labs and workshops. They're incremental, not revolutionary. They're focused on optimization, not defying physics. And they're building a better future, one small step at a time. Let's also acknowledge the role of material science. Magnets are made from rare earth elements like neodymium and samarium. These materials are expensive and environmentally challenging to mine. A truly scalable magnetic motor system must address this issue. Researchers are working on synthetic alternatives and improved recycling techniques. Reducing dependency on rare earths is critical to sustainable EV production. New manufacturing methods, including 3D printed magnet structures, show promise. These allow for precise alignment and minimal waste. Customized magnetic fields become possible with greater control. Again, not perpetual motion, but improved performance. The goal is not just more efficient motors, but more sustainable ones. That's the direction we should be heading. Public interest in magnetic motors also influences investment. Crowdfunding platforms often feature energy inventions with bold claims. Sometimes these attract millions in support. Other times they crash under scrutiny. But even failed projects can inspire discussion and innovation. They raise awareness. They attract talent. They challenge conventional thinking. That's a win in itself. The line between a scam and a misunderstood prototype is thin. We must be cautious but open-minded. Science is about testing, refining, and repeating. If one magnetic motor fails, another might succeed in a different form, especially if it's built with honest intentions and peer-reviewed methods. That's where credibility lies, in transparent experimentation and collaborative research. And the automotive industry is watching. Major automakers are investing in motor efficiency, not just to extend range, but to reduce manufacturing costs. Efficient motors require smaller batteries. Smaller batteries reduce weight. Less weight increases range. It's a positive feedback loop. Magnetic motors, refined, realistic versions, are part of that equation. We shouldn't expect them to change the world overnight, but they can help reshape it gradually, in every motor design iteration, in every performance upgrade, in every battery life extension. That's where the real impact lies. Let's imagine a practical future EV. It uses an axial flux magnetic motor optimized for peak efficiency. It includes regenerative braking with enhanced magnetic recovery. Its chassis integrates wireless charging coils for on-the-go power boosts. The vehicle software adapts to terrain and driving habits to minimize energy loss. All these technologies work together, not in isolation. They form a cohesive, intelligent system. A system that honors the laws of physics but pushes their practical limits. This is where magnetic motors thrive, not in fantasy, but in synergy. They're not a revolution, they're an evolution. And that's okay. If you're still hoping for a true perpetual motion machine, don't hold your breath. But if you want smarter, cleaner, more efficient transportation, magnetic innovation is already delivering, one milestone at a time. The idea of free energy may never become real, but the idea of responsible, optimized energy is very real, and it's here now. We must continue to innovate with integrity, to teach the public how these systems actually work, to separate dreams from deception, and to empower a new generation of engineers. They'll be the ones who refine these technologies further, who understand both the allure and the limitations of magnetism, who design the next great leap forward, not with magic, but with math. And perhaps someday they'll discover something even more incredible. Not perpetual motion, but sustainable mobility for all. That is the real goal. That is the future worth chasing, not for myth, but for mankind. The magnetic motor remains an icon, a symbol of what's possible when imagination meets engineering. It reminds us that energy isn't just about power, it's about potential. And we've only begun to tap into it. This isn't the end of the magnetic motor story. It's just the beginning of the chapter where it finally makes sense, not as legend, but as legacy.